All right, in Chapter 6, Section 5, we talked about constant volume calorimetry. And remember what we used for that? We used a bomb calorimeter, right? Bomb calorimeter. And do you remember what situation that set up for us? Oh man, my vocabulary is a bad way to start a video. Constant volume, right? Okay, so in that we found what did we find? Okay, I don't even remember what we found. All right, so I remember what I was going to say. We found that the heat of the calorimeter was an issue, right? And we could have a heat capacity for the calorimeter and find the change in temperature. Remember that? That was the heat of the calorimeter was the change in temperature times the heat capacity. We also found that the heat that was released by the system was always gained by the surroundings, right? And the surroundings was the calorimeter, right? I think in every situation with a constant volume, in constant volume, the surroundings are going to be the calorimeter, all right? Which I guess then would be what? Minus Q calorimeter, right? All right, so you need to be thinking about that, and that needs to be comfortable for you as you're going through calorimetry. Now we're not in Section 5, we're in Section 7, right? And in Section 7, we're not doing constant volume calorimetry. We're doing We're doing constant pressure calorimetry, which is much simpler actually, right? Because the bomb calorimeter was expensive, right? Remember that? Big apparatus, which required the ability to keep a constant volume, right? Which meant you're going to have some apparatus which is really, really strong in case you have something that blows up inside, right? All right. So with a constant pressure calorimeter, wow, we can just do that on the bench, right? We could just do that at a chemistry bench. Shoot, you could do it at a kitchen table. A constant pressure, right? What's the pressure at my kitchen table where I'm sitting right now? The pressure at my kitchen table at kitchen table is about 1 atmosphere, right? So that's what we're going to be doing. Constant pressure calorimetry, and this is section 7, 6.7. All right. So what do we do? What are we going to use for something like that? Well, we have a neat apparatus that we use for constant pressure calorimetry, which is very inexpensive and very accessible, and it is a coffee cup calorimeter. All right. So in a coffee cup calorimeter, you can see you have something as simple as a couple cups, just a couple styrofoam cups. I'm looking at my notes right now. I didn't have my notes ready. If you hear flipping, it's because I didn't have my notes ready when I started talking. All right. So you have in a coffee cup calorimeter, you have a couple simple, inexpensive cups, right? The whole idea is to make sure that the heat doesn't go back and forth between the outside, right? Heat, we want that not to happen, so we just put a couple styrofoam cups here, a cork lid to keep the heat from going out the top, right? And we measure the temperature of the reaction inside. Okay? So that's it. Now, in a coffee cup calorimeter, what we're going to be doing is we're going to be changing the temperature of the solution, right? So we've got some solution inside, and inside the solution is a reaction, right? And all the heat from the reaction is going to the solution. And so what reaction loses in heat, the solution gains, right? The solution, I think, is always going to be water. All right, so this is what we've got going on here. Q is equal to MC delta T. That is the change in temperature of the water, right? This is the heat capacity of the water, right? And this is the mass of the water, okay? And that is here. And that tells us then, you can see that if we have some water in a coffee cup and we measure its temperature change and we multiply it by heat capacity, which we know it's 4.18 joules per gram degree centigrade. We looked that up, right? If we know the mass of the water because we measure it, we know the temperature change because we measure it. Well, all of a sudden, wow, we just measured all the heat. Okay, where'd the heat come from? It came from the reaction. Okay, and so that's how we do this this problem. Let's do an example. So magnesium metal reacts with hydrochloric acid according to the following balanced reaction. Now, here's magnesium. Here's the water. Right? Can you see that? It's HCl, but it's mostly water, and it gives magnesium chloride plus a gas. Okay. In an experiment to determine the enthalpy change for this reaction, we saw in the last section, by the way, that the enthalpy change for constant pressure is enthalpy change equals the heat at a constant pressure. Remember that? Okay. This is equation 6.12. Equation 6.12 on page 238. Go look that up if you're not comfortable with that. All right. So in an experiment to determine the enthalpy change, which is here, for this reaction, this much metal is combined with enough HCl to make 100 milliliters of solution in a coffee cup calorimeter. All right, so I'm not exactly sure what's going on here. Let's set this up. HCl produces, okay. Looks like there's 2 here. Let's go ahead and make it balanced just in case. Setting up a table, as always, all right. And it says that the mass of the metal is 0.158. Okay, this is in grams. I'm going to get the moles of this right away. This is in grams per mole. And magnesium is what? In grams per mole, magnesium is 24.31. 24.31 grams per mole. I'm going to go to my calculator and say 0.158 divided by 24.31 equals 6.499 times 10 to the negative 3. So it looks like we've got 6.499 times 10 to the negative 3, and this is in moles, of course, okay? So all I've done is just now interpreted this one, okay? So we've taken care of that. Is combined with enough HCl to make 100 mils of solution in a coffee cup calorimeter, all right? So I don't know much about the HCl, but we'll say the total volume right now of everything is 100 mils. You know what? This is of everything, 100 mils. The HCl is sufficiently concentrated so that the magnesium completely reacts, all right? The temperature of the solution, okay. DT rises from 32.8 from 25.6 degrees centigrade, which is equal to 32.8 minus 25.6, which is 7.2 degrees centigrade. Oh wow, we're down to 2 sig figs. You see that? Okay, 2 sig figs. Okay. So, and I know that I'm going to be doing Q of the system is equal to Q of the minus Q of the surroundings. The system is my reaction, and the surroundings is my calorimeter, and the calorimeter is going to be MC delta T, right? And so I'm still reading here. All right, taking care of that. Let's move on as a result of the reaction. Find the change in enthalpy of the reaction. Aha, I'm ready for that. Find the change in enthalpy of the reaction as it is written. Use 1 gram per mil as the density of the solution. Okay, so I've got my volume, and I've got my density, and my density is 1 gram per mil. So my mass then is going to be 100 grams. All right, I'm not going to calculate that for you. I would like you to consider it. You need to see that. All right, if that's not an obvious transition to you, please stop the video and practice that. Okay. So if it's 1 gram per mil as the density of the solution, I've taken care of that. Aha. Okay, and C. Now I've run out of space here. Is equal to 4.18 joules per gram degree centigrade. So let's put this in here. This is 100, and it was 100. That was 3 sig figs here, 4 sig figs here. So it's going to be 100 grams, 3 sig figs. I put that dot there to remind myself of that. Okay, times C, which is 4.18 joules per gram degree centigrade. All right, there's 3 sig figs here. And dt is what? 7.2? Two sig figs here. Can you see that these grams cross off? These degrees Celsius cross off? Okay. And I'm left with, watch this, this is so cool. 7.2. It's 100 times 7.2. You know what, I'm going to do this in the same order as you see it, okay? It's 100 times 4.18 times 7.2, which is 3009.6. 3009.6 joules, which is equal to approximately, it's 2 sig figs, is it? Just 1 second here. Okay, which is approximately, well, you know what, this is not my final answer. Okay, so let's do this. 3.0096 kilojoules, all right? But we were asked to find the, where are we? The heat of the reaction, okay? And the heat of reaction is going to be in kilojoules per mole, right? And I've set myself up. I'm ready to do it right here. Okay, so this is in 3.0096 kilojoules. This doesn't belong in the table anywhere, right? I'm just making some notes here. Kilojoules per 6.499 times 10 to the minus 3 moles, right, of magnesium. But can you see that there's 1 mole of magnesium per mole of reaction? Okay, so this ends up being mole per mole of reaction. Okay, same thing because it's 1 to 1. And I'm going to do that now, divided by 6.499 E minus 3. Okay. Okay, so it comes to 4.63 times 10 to the 2 kilojoules per mole, all right? And I'm going to change my colors to show the answer I'm going to put. Change color to black. And that comes to be, then is approximately equal to, because we're stuck to 2 sig figs. Remember that? That was our smallest one. 2 sig figs. This comes to 4.6 times 10 to the 2 kilojoules per mole is my heat per enthalpy of reaction. And that is it. Lovely. Okay. Hope you like it.